lattice is nothing but a periodic arrangement of points in some space, right? So before we go on to the formal definition of a lattice, where are such lattices used? So some of you from EE are here. We have a course in our second year called electronic devices. And that requires learning some basics about semiconductors and so on. So no thorough study of semiconductors can be done without an understanding of crystals. And crystals are really where the field of lattices shines, because crystals are, although lattices are typically infinite, crystals can be approximated by infinite lattices. So crystallography is definitely one big application of lattices. Apart from that, coding theory, error correcting codes, if I'm not wrong, they also use lattices. And perhaps the application most pertinent to today's talk is in cryptography, which Nilabha will cover later. So lots of applications. Mostly this is linear algebra, slightly more involved. Right, so let me start. What is a lattice? So I need n linearly independent vectors, first of all. So I have n linearly independent vectors such that all of them are in m-dimensional space. Right? So this immediately should tell you something about some sort of order between m and n, because if I have n linearly independent vectors and all of them are in m-dimensional space, that means m should always be greater than or equal to n. Right? Because in an m-dimensional space I can have at most m linearly independent vectors. Right? So this should hold. Once I have this set, I am going to define the lattice generator by this set. And that I will define as L of A1, A2, so on up till An. The set of integer linear combinations of these vectors. So it is the set of vectors that can be expressed as summation xi ai, I going from 1 to n, where xi's are all integers. So I have some vectors and I am taking integer linear combinations. So if I want to say what's the span of this subspace, I typically allow xi's to be real numbers here. I'm not allowing that, I'm only allowing integers. Right? So now, once I have this lattice, one of the bases for this lattice is this set. So, what is a basis? A basis is something that can generate the lattice. So if I have some vectors b1 to bn, I say it is a basis for the lattice gamma if the lattice generated by these vectors is equal to gamma. Right? So before we go into more and more abstraction, let me just take up a few examples. So if I have the vectors in R2, if I have the vectors 1, 0 and 0, 1, can anyone tell me what is the lattice generated by these vectors? Yes? R squared is the wrong answer actually.
Set of all points with integer coordinates.
That is right. So these two, they generate z squared, the Cartesian product of z with itself. And it's easy to see because if I want to generate the point a comma b, I just multiply this by a and this by b and that. Right? So this is one example. We'll come to more examples later. One thing I want to say is you can represent bases in terms of matrices. Right? So if I have, say my basis is a1 to an, I can represent the lattice generated by them as the lattice generated by the matrix A, where A is an n cross n matrix, right? each vector is of an n dimensional space, and n is the number of columns. Right? So I can represent lattices using the basis matrix. Again, this will be sort of a matrix that's like tall in a sense because it has more, n is greater than or equal to n, so it has more rows than it has columns. Right? If I have such a representation, I will use this term. M is the dimension of the lattice, and n is the rank of the lattice. So I have two terms now. M is the dimension and n is the rank. Right? So another special term. If m is equal to n, then it's very nice. M is equal to n. We call such lattices as full rank lattices. Right? Full rank lattices where the dimension is equal to the rank. The basis matrix is really a square matrix, right? Of all integer vectors. So these are some basic terms that are displayed. Now let's go on to some examples. Right, so this is one basis that I have described. I describe another set of vectors. So say my vectors are 1, 1 and 2, 1. Can anybody tell me what is the lattice generated by these two vectors in R2? That is correct. It will be z squared. And you can verify this for yourself. Right? Now we will come to a third example. If I have these two, 1, 1 and 2, 0. What is the lattice generated by these vectors? Do you think it will be z squared?
Sum should be
Exactly. So this does not generate z squared because it can only produce coordinates, points, where both coordinates are integers and the sum of the coordinates is even. Right? So I can't, for instance, generate 1, 0. I can't generate. So clearly, in this example, and this example, all three had linearly independent vectors. Right? All three of them are linearly independent. Yet, some of them don't generate z squared. So a natural question to ask is, when do these vectors generate z squared? So if I have some, just erase this. When do vectors in R2, when do they generate z squared? But in general, if I have some n dimensional space and say for simplicity that I have a full rank lattice, when do n vectors generate Zn? So those are the sort of questions that will answer. Before that, I want to clear up some linear algebra terms. Right? So as I mentioned, we only allow integer linear combinations. So what is the span? The span is real linear combination. So what you would expect from a linear algebraic definition. So if I have some lattice gamma and it is generated by these vectors a1 to an, so then the span of gamma is defined as so if I had two linearly independent vectors, then the span would be R2, right? So this is some linear algebraic terminology I wanted to get out of the way. Another thing that I forgot to mention is if you have this sort of matrix representation, there is also a column space representation for lattices. So if I have say I have a lattice gamma generated by a matrix A. So A is an n cross n matrix. It has n m-dimensional vectors. So I can represent this lattice as does this make sense? I can represent each vector in this lattice as A times the matrix times some x where all the entries of x are integers. Right? So this is just some food for thought that we can represent lattices in this way. Okay. So now that we have some of that in the background, we come to some more terms. So we'll get to the theorems eventually. Some of these terms just are required. Okay, so there is a thing called a fundamental parallelepiped. Parallelepiped, I'm not sure. Some pronunciation. So what that means is if I have some lattice gamma, the fundamental parallelepiped of gamma is denoted as P of gamma. That is equal to, so suppose gamma was generated by some matrix A. So I can represent this as Ax, where x is a vector in Rn such that all of its components are in the interval 0 to 1. Right? So what does this mean? This seems like a very weird definition. So let me just draw a picture for this. I'll draw it here. So let's say I have this lattice. So the regular good old z squared lattice. I should say z squared is really an abuse of notation. It's not square. It's so I couldn't say square, but okay, you all understand. So I have this sort of lattice. My bases are 0, 1 and 1, 0. And say that this is the origin. My fundamental parallelepiped is really this area. So let me just shade it. So it's this sort of rectangle in a more precise sense, a parallelogram that is formed by these two vectors. And you should note that this is one is not included. So this point, and this point, none of them are included in the fundamental parallelepiped. Of course, these lines are included and this area is included. This line and this line again, they're not included. So you should take care. This is not a fully closed set, right? And what's special about this parallelepiped is even if I have some very weird lattice or something like and I have I draw the fundamental parallelepiped. I can tile the span of these vectors by just translating this parallelepiped by each of the vectors in gamma, right? So the span of these vectors that happens to be R2 here. So this could be, suppose in a 3-dimensional space, it could be. So the span R2 can be covered by just taking this parallelepiped and then just translating it. So and you can see that it will tile the plane. Right? So that is one important property that we will exploit later. Right. Okay, so I have defined enough terms for now. Let us come to our first theorem. Right. This is a theorem. So let gamma
of rank n.
right? So it's generated by n vectors, n linearly independent vectors. And say suppose the vectors are b1 to bn. Then okay, so I should really say let gamma be a lattice of rank n. And suppose I have n linearly independent vectors that have nothing to do with gamma. Okay, so I have b1 to bn that are linearly independent. My claim is the following. So I am claiming that n, the lattice generated by these vectors, is equal to gamma if and only if the fundamental parallel pipette contains no lattice points, no non-zero lattice points. So let me just write that down. What is this saying? The fundamental parallel pipette generated by these n linearly independent vectors, if I intersect it with the lattice, I'll get only 0. And this is an if and only if condition. Right? So any ideas on how we want to prove this? So before proving, let's just take a couple of examples. Like someone said, 1, 1 and 2, 0, they do not generate this square. So let's check if this theorem seems to hold. So this is one vector and this is another vector. See, the fundamental parallel pipette actually contains this one. Right? So that means it seems to affirm our theorem. In fact, if we have 1, 1 and 2, 1, we can see 1, 1 and 2, 1. So this will be something like this, and you can see that this parallel pipette contains no lattice points, right? So this theorem seems to hold. Now it is our job to prove it. Any ideas on how we would like to prove it? Okay, so we'll go step by step. So let's do the first part, that's the easy one. So the left to right implication. Suppose I tell you that this is gamma. Now I want to show that this intersection is 0. So what is the lattice? L of b1 to bn is a set of integer linear combinations. And what is the parallel pipette? It's a set of combinations with scalars being between 0 and 1. So now is it obvious that their intersection can only be 0? Because I want scalars that are both integers and in this interval. What is the only such scalar? It will be 0. So their intersection is 0, right? So our one-way direction has been proved. Now let us do the opposite thing. So now given that this intersection is 0, let us prove that this lattice is in fact gamma. Okay, so how do we do that? If I were allowed
You require the linear independence condition to prove it, right?
Yes, that is right. So if I were allowed to have non-integer combinations, I could write any point in gamma, right? So if x is supposed in gamma, I could write x as yi bi, where yi is a real number, right? Because gamma sits in the span of these vectors. Maybe not in the integer linear combination span, but in some span. So I can definitely write every lattice vector as some linear combination where the scalars are real numbers. In fact, there will be rational numbers.
This is only for full rank lattices, right?
Sorry?
This is for full rank lattices.
This is only for full rank lattices. Why is that?
It may be that like in R4 we could have that gamma is a lattice of dimension 2 and V1 and V2 are two vectors and they are like the basis of gamma may be E1 and E2 while V1 and V2.
Right, so you are saying that gamma has to have dimension n. Right, makes sense. So let's consider a full rank lattice. You're right, thank you for the correction. So gamma is a full rank lattice. Now this definitely holds. So if I have any vector in gamma, I can definitely write it as some combination of some linear combination of vectors with the scalars being real numbers. In fact, they will be rational. But anyway, now note that x prime. So I take all of these scalars and I take the greatest integer function. This definitely lies in gamma because all of these are integers. So this will lie in gamma. So now subtract them because gamma, you can think of it as if you have two elements in gamma, their addition will also be an element in gamma. You can subtract these. So this has to be in gamma, right? Because gamma is a lattice. But now this is yeah. So anyways, this is also in the parallelepiped, remember? Because the fractional part always lies in. So this definitely belongs to the parallelepiped also. But what is our claim? Our claim is that the intersection must be 0. So what have we shown? That all of these fractional parts are 0. Which means that all of the scalars that we used were actually integers. Right? Which means that if I have some linear combination, it will belong to gamma. So we are done. We have shown that the intersection is 0 and the lattice generated will be gamma. Okay? Any doubts, confusion? Do you want me to repeat?
Why is that GIF in gamma? You take GIF of Y.
Because these are integer linear combinations, right?
But VI.
So this will be in the lattice. I should say this will be in lattice. Okay? What's the issue?
We are saying that YI is in gamma.
Yes.
And then GIF all is in L of that. So we are subtracting them and then how can we say that?
So you are saying you are assuming that gamma is the lattice generated by Bi in R2. That is what we are assuming. Okay, so I might have made a mistake in the supposition. I should say that yeah. So again, thanks for correcting. I should say that these are all lattice vectors. B1 to Bn are they're all actually lattices. So then this is. Again, thanks for correcting. Yeah. So let me repeat the argument because I got confused. Yeah. So if I have n linearly independent lattice vectors and I want to show that the lattice generated by them is equal to gamma, then this one is easy. This one is trivial to show. But this one, let me take any vector in gamma. I can definitely write it as some linear combinations where all of these scalars are real numbers. Can also write it as not x but some other vector can definitely be written as integer linear combinations of BR because by definition they are all lattice vectors, right? Now take the subtract them. Together the fractional part also belongs to gamma, but this also belongs to the parallel factor. So by definition this has to be 0. So all of the y's are in fact integers, which means that any x in gamma can be written as an integer linear combination of these vectors, which means that bi is a basis. Okay? So sorry for that, I got confused. But is it clear? Is the argument clear? Okay. So we move on. Another question that we might be interested in answering is when two bases are equivalent. Right? So when will they be equivalent? I have two bases. I have two sets of n linearly independent vectors and I want to check if the lattice generated by both of them are the same. So to sort of show what conditions are required, I will be required to define one more term. Right? So unimodular matrices. A matrix U n cross n composed of integer entries is called unimodular if its determinant has magnitude. Right, so some common examples would be 1, 3, 0, 1. This has determinant 1. Another example would be something like 2, 7, 3, 5. Right, because the determinant is minus 8. So all of these are unimodular matrices. 2 by 2 unimodular matrices. Okay. And one important fact is that if U is unimodular, that means that U inverse is also unimodular. I should say U inverse exists, of course it exists because the determinant is not 0. U inverse exists and it is also unimodular. You can go on proving this. What I will just claim is that if you make a cofactor matrix, it will be 1 over determinant of U times the cofactor matrix of U. And it's not too hard to see that all of the entries in the cofactor matrix will be integers. Det of U is just 1 over det of U is an integer again. So this will be an integer. Right? So please, if some of you are interested, please prove this rigorously. I will not be proving it for now. I will come in fact directly to this theorem. If I have two basis matrices B1 and B2, then the lattice generated by them are equal if and only if B1 is B2 times some unimodular matrix. So let's say B1 and B2 are n cross n. So my condition states that B1 and B2 are both related by multiplication of the unimodular matrix. Right, so this is a trivial exercise in linear algebra to prove this. Let me just quickly go over the proof because I have far more interesting stuff to cover. Right, so let's check it one by one. So if I say that the lattice generated by if I take a vector in B2, I can say that it belongs to L of B2. So if Bi is some vector in B2, in the among the columns of B2, then Bi will definitely lie in L of B1. Why? Because any vector Bi is just B2 times the column vector with all zeros and a 1 at the ith position. And this is a vector in the lattice generated by B2, so it must be also in the lattice generated by B1, right? So now every column vector in B2 is an element of the lattice. So can I say that B2 is in fact B1 times some n cross n matrix C? Can I claim that? Because I can do this for all columns, and then whatever is, say, Bi is B times Ci. Then I can collect all of these Ci's together and I can make this matrix C. Right? So I can definitely claim B2 is B1 times some C. Alternatively, I can also show that B1 is B2 times some other matrix B. Using the same argument, but showing that every column vector in B1 belongs to the lattice generated by B2. Okay? So now once I have these two, I will now proceed on to the other part. So B1 is B2D, which is B1 CD. Consider B1 transpose B2, B1 transpose B1. That will be B1 CD transpose B1 CD, which is equal to CD transpose B1 transpose B1 and prime CD. Getting the determinant. Because if I have a multiplication of square matrices, note that all of these matrices are in fact square and they will be of the same order, n cross n. Then I can, the determinant is multiplicative, right? Determinant of CD transpose is equal to the determinant of CD. So this is just determinant of CD squared and times this one factor. Determinant of B1 transpose B1. Now, by definition, because B1 is a basis, it is generated, it has n linearly independent vectors, and it is not too hard to show that if B1, that is n cross n, and all of its columns are linearly independent, then you can in fact show that this value will never be 0. So you can cancel this. Again, I will encourage you to prove it rigorously. I will not do it in the interest of time. So the determinant of CD squared is 1, which means that the determinant of CD is plus or minus 1. Because C and D are both integer matrices, as we showed. Because both of them are integer matrices, and the product of two integers is plus or minus 1. Both of them must individually be plus or minus 1. So both C and D are unimodular. That completes our proof. And once you have this direction is sort of the harder direction to do. The reverse direction is not too difficult because you already know that every column vector in B1 belongs to the lattice generated by B2. Similarly, I can write B2 is equal to B1 U inverse. We have already shown that if U is unimodular, then U inverse is also unimodular. So every column vector in B2 will also be in the lattice generated by B1. So that means that B1 and B2 actually generate the same lattice, thereby completing our proof. Okay? Any doubts? Any confusions? Repetitions required? Right? Okay. Let me move on. So now we have to talk of a slightly more abstract concept. So if I have some lattice generated by a basis matrix A, I can talk of the volume of the not the volume, the determinant. So we already have defined determinants for matrices. Now we'll define determinants for lattices. What is det of gamma? That is defined as square root of the determinant of A transpose B. And if gamma is a full rank lattice, then this will just be equal to the absolute value of the determinant of A. Right? Now what does this represent? So this represents the n-dimensional volume of the fundamental parallelepiped of gamma. So if I say unity of gamma, I should really be writing A because that is how I define my basis. The fundamental parallelepiped of these basis vectors, इसका n-dimensional volume is what we quantify as determinant of gamma. Now what does volume mean and so on and so forth are questions that we will not go into. So it's easy to see that this really does not depend on the basis. So if gamma had some other basis, so if you know A1 and A2 were both basis for gamma, then you can show that in fact det of A1 is equal to the determinant of A2 in absolute value. Why? You can write A1 as A2 times some unimodular matrix and you just compute this, right? So this is for full rank lattice. You compute this for both of them, U transpose ka determinant will always be 1, so that will cancel. So this really doesn't depend on the basis, and you should think of this as, so if you have some ball, there are some large ball, say K. What does ball mean? Won't go into that. There are some ball K in the span of gamma. Then you can think of the number of lattice points in K. Lattice points in K. Approaching volume of K divided by det of the lattice as the size of K increases. So that is really what you should think of this determinant as. It makes sense, right? Because each lattice point will have some parallelepiped, and in general, the number of lattice points will be the number of parallelepipeds that contribute to the volume. Right? So that is how you should think of it. Okay. Before we move on, and I promise this is the last time I'm going to bore you with linear algebra. Right? I would like to cover Gram-Schmidt orthogonalization very briefly. Second year students will of course have done it. First years, I don't know, have you done GSO in your MA110 now?
No.
You have?
No.
We haven't. Okay. So touch upon it briefly. I won't prove it, of course. So GSO is a process that takes some n linearly independent vectors and converts it into another set of n linearly independent vectors. where all of these entries are defined as follows. So A1 in the new set is equal to A1 in the old set, and AI in the new set is defined as AI minus the summation from 1 to I minus 1 mu ij a j in the new set, where mu ij is sort of the projection of the j vector on I. So that's AI aj I'm sorry, this should be here. This is your regular inner product that we defined. And so this projects each vector here. So consecutively. So you should really think of this no longer as a set but as an order tuple. It projects every new vector into a space that is orthogonal to the span of the previous vector. That is what all these coefficients are telling us. Right? So it's used to generate orthogonal bases out of non-orthogonal bases. Okay? So some properties that I won't be proving. Orthogonality, if I is not equal to j, then the dot product of those two vectors will be 0, so they will be orthogonal. The span is invariant. So if I consider the span, it doesn't really change during this process. This is not a property, but regarding lattices, you should not expect these vectors to lie in the lattice, right? Because mu ij might not be an integer in general. It could be, but we don't demand that. So this set need not be in the lattice. Not a property, just confirming that. And lastly, this is a sort of curious property. So if I take the determinant of the lattice made by these vectors a1 to an, that will be equal to the product of the magnitudes of these new vectors. So ai please prove this. I will not be proving it. In the interest of time, I'm already proving it. Right, so these are some properties that I'll keep on this board. We'll come back to this when we discuss Gaussian reduction on lattices. Right, so now we'll move on to successive minima. So what are successive minima? Define that. Successive minima. So when we Nilava will be talking about it shortly, but the reason why lattices are useful in cryptography is because there are two problems that we'll discuss, SVP and CVP. We'll come to that. And they are computationally very difficult, and they involve a notion of length in lattices. So what is length? It really means nothing different than the regular Euclidean norm. So the length of some vector x is defined as the sum of the components squared. So the Euclidean length that we consider. So now I want to define successive minima. So I'll go slowly. Lambda 1 of gamma is the length in the Euclidean norm of the shortest non-zero vector in gamma. Right? So this is length of the shortest non-zero vector in gamma. Very easy definition. But for successive minima, right? So now I'll define lambda I of gamma. Right? This is a very complicated definition. It is the infimum over R, where R is a positive real number and the dimension of the span of gamma intersected with the closed ball centered at the origin with radius R is at least I. Right? So let us unpack this definition slowly. First of all, what is this ball? So the ball, so there are various types of balls that we can define in RF. One of them is the open ball, that will be B0R. The set of vectors such that the length, the distance between them and 0 is strictly less than R. This is the open ball. The closed ball will be considering the boundaries as well. So the closed ball is right. So that is what this means. I want to consider R is some quantity and I want to consider the closed ball of radius R centered at 0. I want to consider the intersection of that ball with gamma. So the vectors which are in this set and in this set. So there will be lattice points inside of or on the boundaries of this closed ball. The span of that set should have dimension at least I. So why didn't I just define it as the, so what I want to say is that this is the second shortest, the length of the second shortest vector. Why didn't I just define it like that? The problem is if I have one basis vector which is like small in length and another which is large in length. And somebody asks you to find the length of the second shortest lattice vector. This is obviously the first, so this length will be lambda 1. If I were to define it as the second shortest, then that would be this length. But we don't want that. We want vectors which are not in the span of the vectors which already have lengths of previous minima, right? So we want to consider this instead. So that is why we require that the span of the lattice points that are in this ball of radius R should be at least I. Why should it be at least I and not equal to I? Because if I'm in 3 dimensions, I am allowed to have 2 vectors that are equal in length. So if I were to define lambda 2 and lambda 3 in suppose 3 dimensions, and if they turn out to be equal, that is not an issue. So in fact, in that case, even whilst defining lambda 2, the dimension will be 3. It won't be 2, right? So we want this, we don't want an equality. And of course, this minimum is the infimum of all such radii, right? So what I want you to think of it as, you have a large ball and you are sort of slowly reducing its radius, and you stop and you realize that you have enough lattice points in your interior which span a subspace of dimension at least I. That is when I want you to stop, right? So that is the definition of successive minimum. We have this theorem now. So if A is a rank n, so if gamma, A should be, this should be a set of n linearly independent vectors, okay, and let A tilde be its gram-shaped orthogonalization. Then the result that we will be using is that read this. So the shortest vector is actually greater than the minimum Gram-Schmidt orthogonalized vector, right? And if you want to look up the proof or do it yourself, feel free to do it. I will be skipping it because I really need to cover this one algorithm. Otherwise, I will shout at me. Right. So the reason why I introduced this concept of successive minima, there are two corollaries. Again, I'll not be proving this. Feel free to meet me after if you want to see a proof. Corollaries. So gamma is a lattice. Then there exists some epsilon greater than 0 such that for all vectors in that lattice not equal, they are at least epsilon apart. And what is a good candidate for this epsilon? The first successive minimum. Because we know that the distance between two non-zero vectors is also in the lattice, and that by definition is non-zero. It will have a length of at least lambda 1 of gamma. Right? Here. The length of the shortest non-zero vector in gamma. This is one important corollary. Another corollary that is very easy to see is that all of the successive minima are actually achieved. What does that mean? There exists a vector x in gamma such that the length of x is equal to the ith successive minimum for all I. Why is this true? Because I defined lambda I, the ith successive minimum, as the infimum. So if I hadn't defined this, maybe there would be no such x for which this would be achieved. I could just take a larger ball, but I have defined it as the smallest one. That means there must be some vector which achieves this. Okay, that is another important corollary, right? And this sort of concludes all of the math that is essential for dilemma solving. Now I will describe one algorithm in detail. So coming to cryptography. Right. So there are really two important problems that are in lattice-based math that are important in cryptography. Right? And those are SVP and CVP. So SVP is the shortest vector problem, and CVP is the closest vector problem. So what is the shortest vector problem? It's simple. Given a lattice, you have to determine the shortest vector in that lattice. Right? So there are three variants. So if you have a lattice, say generated by B, find a vector B in this lattice such that the length of B is the first successive minimum, that is the shortest. So you have to find a vector which achieves its length being the shortest, being that of the shortest non-zero vector in the lattice. This is one problem. Another problem is optimization. Find the shortest vector. Given a lattice gamma, the length of the shortest non-zero vector ring. And the third one is decision. If I have a rational number, how does it compare with the length of the shortest non-zero vector in the lattice? So given, not necessarily rational, given some r, decide if the length of the shortest non-zero vector in gamma is at least r. So these are three problems, and in general these are very hard to do. We'll describe an algorithm to do it in 2 dimensions. So the fact that these are computationally hard to solve is really why we are using it. So there are certain theorems that bound these quantities. So I will just state this theorem once. It's called Minkowski's first theorem, because mathematicians like Gauss, Lagrange, Minkowski, Lichtenfeld, all of these worked on lattices. All of them have theorems named after him. Minkowski's first theorem. I'll just state it. Of course, the proof requires another theorem that we won't be able to prove due to lack of time. It states that for a full rank lattice, that is gamma, the length of the shortest non-zero vector in gamma is bounded above by this quantity. When n is the rank of the lattice. Right? So we have some upper bound for the first successive minimum. But even though this is a bound, this doesn't tell us how to compute it. How do we actually find what this value is, or how do we find vectors which achieve this length? So it doesn't give us any algorithm. So this proof is. Yes.
For the search column, could you give an example where the small b is not equal to the shortest vector in capital V?
Sorry?
Could you give an example where small b is not equal to the shortest vector in capital V?
No. So this is what we are trying to do.
Yeah,
So these are all problems. So they're not.
Yeah, no. The answer is obviously not to just find the shortest vector in B, right, in the basis.
Yeah, it is to find the shortest non-zero vector in B. Or it is to find our shortest non-zero vector in B.
Shortest non-zero vector in the lattice, right?
Yeah, in that. In
So
the lattice.
why won't it be the shortest non-zero vector in B is what I can't understand. So could you give an example where that is not the case?
So I'll give you a homework. Consider the lattice generated by, and I want you to do this because you've asked it. Find the shortest non-zero vector in this lattice. I describe an algorithm as to how to do it. But it's clear that my basis vectors could actually be quite large. In fact, as you'll see, if you actually do the computation using the algorithm that I'm about to explain, the smallest vectors are very small. They're in the thousands range. Whereas all these basis vectors are in millions, lakhs, I don't even know, lots of digits, right? So it's not trivial to find the shortest or to find our shortest non-zero vector in the lattice. Okay? Right. So now we'll come to Gaussian reduction. Sorry, I'll take 5 more minutes. CVP is similar to SVP. It's not exactly the same. CVP requires you to find the lattice vector that is closest to a given lattice vector. also called Gaussian Lagrangian reduction on lattices. So if you are given a full rank lattice of dimension 2, so this algorithm is best suited for dimension 2, and you are supplied with a basis for gamma. So gamma has some basis. So I'll describe an algorithm now. Wait, let me just read it off here. Continuing this algorithm here. I hope this is readable. The thing not too much. Is it not obscuring is the dirty board not obscuring the text? If n is 0, then you return a1. Otherwise, you put a2. Right? So you are given a lattice, a full rank lattice with dimension 2. You have given some basis. Gaussian reduction aims to do two things. One is it solves the SVP, right? We will come to the theorem. It solves the SVP, and further it gives us a nearly orthogonal basis of short vectors. So small vectors which form a nearly orthogonal basis. Right? What is the algorithm? I have given this basis. An interval. If A2 is less than A1 in magnitude, then stop. So I want A1 to be the shorter vector. Then you define this quantity M. What is M? M is really the projection of A1 on A2. So it's similar to, so you can see that this process bears some resemblance to Gram-Schmidt orthogonalization. But I'm taking this, so this is the symbol for rounding to the nearest integer. Right? So so typically you would find, this is the floor, this is the ceiling. So I'm using this notation to denote that it has rounded to the nearest integer. If this nearest integer is 0, then you return the vectors and close the program. If not, then you replace A2 with A2 minus M times A1. So it's sort of subtracting the largest copy of A1, so the largest integer copy of A1 from A2. That is what it aims to do. And then you repeat the loop. What is the theorem associated with this? Theorem is that this algorithm, Gaussian Lagrangian reduction on lattices, solves SVP. Which means that when the program terminates, A1 is a shortest vector in gamma. Right? So you can deterministically solve the SVP for two-dimensional lattices using Gaussian reduction. Okay? How do we prove this? It's not that difficult. Okay? The proof. Suppose that it has terminated, So what am I returning? I'm returning A1 and A2, and I'm only returning them if M is 0. So what are my conditions? So if I have A1 and A2, then A1 has to be less than A2 in magnitude. So A1 is less than A2 in magnitude. Also, M is 0, which means that A1, A2, and the modulus of A1 square.
A1 is less than equal to A2.
Right. A1 is less than A2. Okay. Thank you for the correction. And this is 0. What does this mean? That if something rounded to the nearest integer is 0, that means it's at most half, right, in magnitude. So the modulus of this quantity A1, A2, A1 square is less than or equal to. So another thing that you can prove apart from this theorem, which is like sort of a corollary, is that when the program terminates, the angle between A1 and A2, because we are only talking about two-dimensional lattices, right? So we can define an angle. The angle between A1 and A2 will lie in this range, so pi by 3 to 2 pi by 3. And I think you can see that already because this is cos theta. Cos theta is less than half in magnitude. I think this is 4. Right? So just check that once. I think it's not that hard to do. Now I have these conditions. So A1 is less than A2, and then this is 0. Now I will show that A1 is actually the SCP. Is the transfer. So say any non-zero vector A in the lattice. The idea of the proof is to express A in terms of A1. How will I do that? I write A as alpha A1 plus beta A2. I can always do this because I have given that A1 and A2 form a basis. And we have a couple of steps of algebra, which is alpha square plus 2 alpha beta times the dot product of A1 and A2. Right? Now, this will always be greater than or equal to the following quantity. What is the quantity? The mod idea is the mod is alpha square minus 2. This is the other case. Here the main modulus minus 2 mod alpha beta mod of this term. Is this obvious? Because if I have a quantity, it will always be greater than or equal to the additive inverse of its absolute value, right? This makes sense. I can this I already have some upper bound now. So this will be greater than or equal to alpha squared plus beta squared minus the 2 will cancel from there. So minus alpha beta A1 square. I know that A2 is greater than or equal to A1 in magnitude. So this will be actually greater than or equal to alpha square plus beta square minus modulus of alpha beta times the modulus of A1 square. And then it's a trivial exercise in number theory or whatever, algebra, to show that this cannot be 0. The only way it's 0 or something lesser, it can't be lesser, you can show that for yourself, it's I think AMGM will do it, is if both of these are 0, but by definition A is not 0. So if alpha and beta both 0, then A is 0, that's a contradiction. So this is not 0, so it's strictly greater than 0, this is an integer, so the only integer that Any integer that's greater than 0 has to be at least 2, right? So it's greater than equal to mod of a1 square. Again, please make sure that this actually holds. Verify it for yourself. So what I've shown is that any non-zero lattice vector is at least a1 in magnitude. But a1 is a lattice vector that is a1 in magnitude. Therefore, a1 solves the SAT. Right, and this is homework for you. Please use this algorithm, especially you. Please use this algorithm and get back to me with the shortest vector. Okay? Or shortest. There are a couple of other theorems I wanted to discuss, but I've already exceeded my time. So now I'll call Niranga to continue the talk.